In this video we're going to be looking at integration as the limit of a sum. And I'll just read what it says. You can approximate the area under a curve as a number of thin rectangular strips. This is going to be a similar concept to trapezium rule if you've seen and worked through trapezium rule. But rather than using trapezia, we're thinking about rectangles. As you make these strips narrower and narrower, the approximation becomes more accurate. You can use limit notation to formalise the idea of a definite integral as the limit of a sum of areas of these rectangular strips. This essentially is the exact definition of definite integration. So just to understand what it's telling us there, if we look at this diagram below, we've got a curve and it says we can approximate the area under a curve using thin rectangular strips. Well, I've started with some thin ones there, so we can calculate the width and the height and do the area of each one. But you can see that it's not going to be the best approximation because the rectangles are going above the curve and also maybe missing a little bit below hand as well. So if I make those widths of the rectangles smaller and smaller and keep reducing the size of the width of the rectangle, I'd like to think that my rectangles are more like these ones where you can see they're almost going to just thin lines, thin strips. And if I put all of those together, they will start to form an accurate answer for the area under that curve between the two limits. So this is called integration as the limit of a sum because you can see the limit and you can see summation. So essentially, if you see this notation in a question or in the exam, you can just write this part over here. Okay, so do definite integration what you're used to. I'm just going to explain the formula a little bit. So we've got limit. We've seen limit when we've done differentiation by first principles. So we've got the limit because we are wanting to think about the widths x becoming narrower and narrower and getting that small that they're tending towards 0. If we actually calculate the area of the rectangles, it'll be the height, so in our case f of x, the height of these rectangles, times by the width x. Now we've got these Greek letters here, delta, and that just means the small change in x. So the width, and like I say, we want the width to be really, really small, tending towards 0. And that would be for one rectangle doing the height times the width, but then you'll have to add up all the rectangles between your limits, so between x is a and x is b. So essentially, if you see this in a question, you can write or rewrite it with definite integration and then just do the question as normal. So let's have a read of the first example. The diagram shows a sketch of the curve with equation y equals sine x. The area under the curve between x is 1 and x is 2 can be thought of as a series of thin strips of height y and width delta x. Calculate this, giving your answer correct to 4 significant figures. Now, the minute I see this, I will write it. I'm going to make it equal to the integral between 2 and 1 of sine x dx. So that's all we have to do for these questions. Change it to definite integration. Keep this the same, keep your limits the same, and put dx at the end. So from here, a very nice integration it should be. If you integrate sine x, you get minus cos x. Then put the limits, and I will substitute in the limits. Now working in radians, we're integrating with trigonometry. So I'm going to get some decimal answers here. I'll write them out as much as I can. Just checking the last few digits. And then if I sort that out to 4 significant figures, I get 0.9564. Now, if you were to check that on your calculator, so use the integral button, remember that's very helpful. You just type this in as it is. The calculator gives you an answer of 0.9564, also to 4 significant figures. And if you've done trapezium rule, your calculator answer isn't the same as your trapezium rule answer. That's because you are using an approximation. Here we are no longer approximating, so we will get the same answer as the calculator. You can see that we've got equal signs rather than approximate signs. Okay, so I am expecting to get the same answer on my calculator, which is useful for checking purposes. If we go to number 2, I'm going to leave that one with you for a minute. Just pause the video, rewrite it in terms of a definite integral, and see how you would go about integrating x root x minus 1. Okay, so pause now. Okay, if you've had a think about it then, I would have written my definite integration. I would have wrote probably x root x minus 1 and then change it to what I've written there. Now to integrate that, I used substitution. So I made u equal x minus 1. So if you've paused it enough and done it all, I'm just going to work through it now. If you're unsure, just be writing it down, what I've done in your notes. So I let u equals x minus 1. Then I differentiate u to get du by dx, which in this case is 1. And I do that because I want to find a replacement for dx. So when I times both sides by dx, I find that dx is equal to du. So I'll be able to substitute in u into here and du there. I also have to change the limits if I'm making an integral entirely in terms of u and integrating with respect to u. The limits are in terms of x. So I just use the fact that u equals x minus 1. So if x is 10, u is 10 minus 1, which is 9. If x is 5, we've got u is 5 minus 1, which is 4. Then if I start to substitute in, you can see I have changed the limits and I've got x times u to the power of a half du. I have to replace the x bit. So once I've simplified everything, I've still got x. I need the whole integral in terms of u. So if I go back over this side, I rearrange u for x. So x is u plus 1. So you can see I've put u plus 1 into there. Now if I expand, I'll get u to the power of 3 over 2 plus u to the power of a half. And then it's going back to some nice year 1 integration from here. So just add 1 to the power, divide by the new power for both terms. And then I'm substituting in the limits 9 and 4. So when I do that, you can see I'm doing that here. And then sorting it out, I've left it as an exact value. It does ask me for an exact value, so watch that wording. An exact value would be a fraction, so I've left it as that. Now feel free to pause the video. If you're still copying down, you can pause, rewind, so it's on the correct part that you need to copy down. The last question to look at is this one here. So if we read it, it says the diagram shows a sketch of the curve with equation y equals the cubed root of x, where x is greater than 0. The area under the curve between x equals 2 and x equals 5 can be thought of as a series of thin strips of height y and width delta x. Calculate this, giving your answer correct to 4 significant figures. Now I've done 2 examples. See if you can pause the video and have a go at this question yourself. Rewrite the limit part as the definite integration and then see if you get the same answer as me at the end. Okay, so if we look at this together, let's rewrite the integral as 5, 2, and then x to the power of a third. That's a nice integration to do, so add 1 to the power, divide by the new power, substitute in your limits, and you get 4.523 to 4 significant figures, and you can check again with your calculator that you do get the same answer as what you got as well. Okay, that's the video done.